Toasters?
Oh my God.
Okay, we finished this one. We talked about it right to the end of the bell. Later on in the year, we're going to be studying something called improper integrals. And an improper integral, it could be something like this. We're finding the area of an unbounded region. And sometimes it's finite and sometimes it's infinite. And that's why the end of the year is so much fun, because we start studying all the contradictions that are involved when you work with infinity and zero. And some of them kind of are irreconcilable in your head. So it's fun. It's fun. Some people think that that's why the end of the year is so challenging with the material, but just think of it, that's why the end of the year is so much fun. Okay? Keep that in mind. All right, so we'll space bag this. Okay, still there if we need it. It's just under the bed. All right, so x to the fourth. This is one where maybe we could easily do some calculus, but maybe we know what the graph looks like. Anyone know what the graph looks like? Yep, like that, just like that. They made hand motions that resembled the graph. Okay. It looks a lot like x squared. Very good. This would be -1. This would be +1. The only difference is between -1 and 1, the graph of x to the fourth in relation to the x-axis is what? Closer or further away? Closer, because between -1 and 1, like let's say 1/2. 1/2 squared is 1/4, but 1/2 to the fourth is 1/16. So it's closer to the x-axis between -1 and 1. And then outside -1 and 1, like at 2, 2 squared is 4, but 2 to the fourth is 16. So it's steeper. It comes in a lot steeper, and then between -1 and 1, it actually gets closer to the x-axis. And it goes like that. Symmetrically. You get the idea, right? It has y-axis symmetry. Mine does not. But it kind of looks like a graph of x squared that's kind of sagged a little bit between -1 and 1 over the years because of the gravity. You know, it could happen. Now, if you're just looking at this, you can answer pretty much all the calculus questions, can't you? This function is decreasing from -infinity to 0, increasing from 0 to infinity. We have a local min and an absolute min of 0 at x equals 0, right? And what about the concavity? Any inflection values? 1? An inflection value would be where the concavity changes. It doesn't change. This graph is concave up like a cup everywhere. So do we have any inflection values? No, we do not. Okay, so let's look at what the calculus would tell us. G prime would be 4x cubed, right? Hello, G prime. If I set it equal to 0, I get a free critical value right away, right? And I knew that. There's 0. I can see on the graph that it's a critical value. I know it ends up being a local min and an absolute min. G double prime is 12x squared. Is that ever undefined, 12x squared? Is it ever 0? Yep, it's 0 when x equals 0. Notice that means it's a PIV. Hey, is every PIV an actual IV? Is every critical value a local max or min? No. We saw a PIV in the warm-up that wasn't an actual IV. Here's another one. If you were actually to do the number line chart, you would see that G double prime is positive on both sides. In fact, oops, not there. G double prime is positive for all x not equal to 0. So here's an example of a value that will come out of the work when you're doing the second derivative, but it's not an actual inflection value. So just keep that in mind. I know y'all are good at keeping everything in mind, right? All you have to know is everything on that poster over there, and realize it's two sides. And then there's probably more, too, that didn't fit on the... There's another side. Yes. Okay. So just keep it all in mind. Let's see if the second derivative test will work here. If I took my critical value of 0 and I looked at the concavity at 0, what's the concavity at 0? It's 0, right? If you plug a 0 into the second derivative, you get 0. In fact, we got 0 from setting it equal to 0. So if the concavity is 0, that doesn't really tell us much, right? In fact, we know that the function should be concave up at 0, right? But when you plug the critical value in to the second derivative, you get 0. That's not a positive number. So you're going to see that that's one of the downsides to the second derivative test. It doesn't always work. And you have to have the second derivative, but it can be really nice sometimes. Okay, that's all I wanted to do about that one, is just to show you another example of a PIV that's not an actual IV. And there's more. Now, something like this we can answer very quickly because the cube root of x is now one of our parent functions, right? Remember what it looked like? Came in like this, and at 0 has a vertical tangent line. But instead of coming back out like that and making it a cusp, what does it do? It increases through it. Yeah, it's an origin symmetric function. The derivative at 0 is undefined, but it's continuous everywhere. We were on cusp alert from the beginning, weren't we? Because that's the same as x to the 1/3. Now, in this case, when we say cusp alert, we mean vert alert, right? Because that's what a cusp is. It's where we have infinite slope. It's a potential cusp. Do we have all the calculus questions answered from this graph? The function is increasing where? This would be first derivative info. Everywhere, right? You could say for all real numbers. Even though technically at 0 it's undefined, the slope, you could say that it's increasing through that singularity. For what values of x is the concave up? Negative infinity to 0, and the concave down from 0 to infinity. Yeah. Do we have any inflection values? Well, an inflection value is a point on the graph where the curvature changes. Yeah, it's at 0, right? Now, look what the calculus, if you just did something like this purely analytically, f prime would be 1/3 x to the negative 2/3, right? And we know that would jump down to the bottom, and we wouldn't have any values that made it equal to 0, but it would be undefined at 0, and we know to look for those. The second derivative would be negative 2/9 x to the negative 5/3. Now, if we're talking about concavity, if I clean that up, that's negative 2 over 9 cube root of x to the 5th. And without knowing what the graph looks like or thinking about it, a lot of students might say f double prime equals 0, never, never. And so they would walk away saying there's no PIVs and thus no IVs, no inflection values. And they would be what? Wrong. Because it's not just where the second derivative is 0, it's where the second derivative, just like for critical values, is undefined. And that's going to be when x equals 0. As long as they're in the domain of the function, and this one is. So keep that in mind also, right? It's not just where either derivative, depending on what you're looking for, first or second derivative, critical values, PIVs, is 0, it's also where it's undefined. All right, so if you did a number line chart, you would see that it comes out to give you the same conclusion as the graph. So far, so good? Oh, so good so far. Okay, last one. Piecewise. Oh, I love piecewise. They're the exception to every rule. Piecewise are probably just usually better just graphing them. Is it continuous at 0, this function? Why is it continuous at 0? Yeah, the limit from the left is 0, the function value is 0, and the limit from the right is 0. Bless you. So is it connected? But how is it connected? Is it smoothly connected? Bless you. You could either take a piecewise derivative and take the limits of y prime from left and right, or you could graph it. To the left of 0, and at 0, it's the square root of negative x, which would start at the origin. And what does the negative in front of the x do to the graph? Y-axis reflection, so it opens like this. And then x squared, of course, I know it shares the point at the 0. It opens like that. Cool. That might have been how you learned to make a cursive V back in elementary school, right? Something like that, right? It's a V. Is it differentiable at 0? No, and the graph tells us that pretty easily without having to take the piecewise derivative. Bless you. We know the calculus questions then, don't we? This function is decreasing from negative infinity to 0, increasing from 0 to infinity. Do we have a critical value? Where's the critical value, Tally? 0. Is it a local max, local min, or local neither? Yeah, one of those three. Bless you. It's a local minimum, right? Local minimum. But that's going to be a critical value where the derivative fails to exist. Do we know the concavity questions? The answers, I guess. This graph is concave down to the left of 0, concave up to the right of 0. Do we have an inflection value then? Yeah, it's at x equals 0. Okay. So it showed up as a critical value. It also showed up as an inflection value. Can critical values also be inflection values? Sure. Sure. Right there. There you go. And you would find it, if you were to take the piecewise derivative, it would be where both of the derivative and second derivative would be undefined. Okay, speaking of victory, man, we earned that one. That was a long problem. It had A, B, C, D, E, F, G, H problems. Okay, let's talk about the second derivative test formally now. I've been alluding to it. The second derivative test is not a test for concavity. If you're asked to determine intervals of concavity, it'll say determine the intervals where the graph is concave up or down. The second derivative test is like the first derivative test. It's a test for local or relative extrema. Okay, the only difference is it uses second derivative information to determine it rather than first derivative information. So here's what it says. It says, let f be a function such that x equals c is a critical value of f. So we already have our critical values in our hand. We've already taken the derivative, we've set it equal to 0, we've seen where it's undefined, and we made sure they were all both in the domain. We have those x values, call them x equals c. If then we plug them into our second derivative, and it ends up being positive at that critical value, then what does positive mean? It means that it's concave up like a cup. And because it's concave up like a cup and it's a critical value, it's got to be a local minimum. Okay? If at a critical value the second derivative is less than 0 is negative. So that means like Walter, we're concave down like a frown. If it's a critical value, it's got to be a horizontal tangent, so it's got to be at the top there. It's going to be a local max. So that's what's good about the second derivative test. It requires only one calculation at the critical value instead of one on either side. But there are downsides to it. It doesn't always work. If the second derivative at the critical value is 0, it may be a local max, it may be a local min, it may be a local neither. It's inconclusive. So concavity not test works not, so you panic, right? These are supposed to be like zeros in his eyes. He's panicking. If you get a 0, you panic. I used to draw it, but then I remembered Macaulay Culkin. Yeah, his younger brother is in the new Fargo series, or was in the new Fargo series. Yeah, he was in the new Fargo series. So what happens if the second derivative test is inconclusive? Well, you go back to the first derivative test, and you test the slopes on either side. All right. All right, so let's jump ahead to example 5. We're going to try this out. Find the relative or local extrema for this function using both the first and second derivative test. We'll compare and contrast, and we'll write like a 5-page essay discussing the benefits of each of them and the downsides as well. And then we'll share papers and see if we can convince some non-believers. What are we going to need first? Both tests require that we have what in our hand? Or in our other hand? We need the critical values, right? We need the critical values. So the domain of this function f of x is what? All real numbers all day long. So we'll find the critical values by taking the derivative. And again, you don't need of x unless you're actually plugging in, so it's a little more economical. You get negative 15x to the 4th plus 15x to the 2nd. And, of course, we always consider first where it's undefined. And where is this undefined? Nowhere. So now we can just set it equal to 0. And I'll go ahead and factor out a negative 15x squared, which leaves a negative x squared. Positive, sorry. That's the whole purpose of factoring out the negative. Positive x squared minus 1. Now, I said yesterday that if you get to something like that, the whole purpose of factoring it is to help us identify the zeros and to plug back into. I think we can handle it with x squared minus 1. Once you set it equal to 0, then, when you say x equals 0, and what are the two others? Negative 1 and positive 1. Bless you. You're implicitly declaring those to be critical values, CVs. You don't have to say they're CVs. When you take a derivative and you set it equal to 0 and you solve for x, you're saying they're critical values. Now, the first derivative test requires us to test between them. If you wanted to look at it in full factored form, let's kind of tie something into what we did in the warm-up. Just like with the second derivative, if you were to plug each of those three values, bless you, back into the number line, notice the powers on the factors that generated those zeros. At x squared, when x is 0, do you think you're going to see a sign change on either side of 0? Remember, 0 is generated by this factor because it's to an even power. the graph of this function is actually going to bounce, just like x squared would, on the x-axis at 0, which means it's going to be the same sign on both sides, maybe positive, maybe negative. But again, if your exponent is positive on the factor, you will not see a sign change. But if it's an odd exponent on a linear factor, you will see a sign change. So of the three, which two are going to be local max and or mins? Just one and negative one. Now, to determine what type they are, you're probably going to want the sign change, and the table is a good way to organize that. So we'll just see if that comes out to be the case here. We're talking about f prime, so pick your favorite numbers or your least favorite or something safe. -2, -1/2, 1/2, 2. And again, being very careful about it, you don't have to plug into the x squared. You're just going to plug it into x squared minus 1 and then change the sign. You could even distribute the negative into the x squared minus 1 and call it 1 minus x squared if you want, and then you're just looking at one piece. All right, I'll look at 2. Plug in a -2, and I get 4 minus 1 is positive 3 times negative is negative. A negative 1/2 squared is a positive 1/4. Minus 1 is negative times negative is positive. Now notice that your derivative is an even function. You see that? It's x squared and x squared. So plugging in a positive or a negative is going to give you the same answer. So you should get a positive or a negative. So there are ways to kind of be a little bit more efficient as you plug into these things. But the bottom line is if it's factored, go ahead and plug into the whole thing if you're not sure, and make sure you just get the correct sign. And as I told you, at 0, we don't see a sign change. The factor was squared, so there's no sign change. It happens to be positive on both sides. So by the first derivative test, we'll say f has a local minimum. If you want to draw them like that, I still like to draw them so I can see them. A local minimum at x equals -1, since f prime changes from negative to positive. Where? Where does it change? At the same place, at x equals -1. And at x equals 1, you would say f has a local max at x equals 1, since f prime changes from positive to negative at x equals 1. Occasionally, you might have to make an argument for all the critical values, whether they're local min, local max, or neither. Here's what you would say for 0. F has neither a local max nor a local min at x equals 0, since, and it has to be a local argument, since f prime is positive on either side of x equals 0. That saves you from having to write out that long word, since x is positive immediately to the left of 0 and immediately to the right of 0. You can just say it's positive on either side of 0, and the word either embodies and encompasses the whole local feel of the argument, right? Yeah? Now the first derivative test worked beautifully there. Why would we want to do the second derivative test? Well, it's nice to have options sometimes. But you know what? The second derivative test requires having the second derivative. And do we have it? No. So let's go get it. Now, I would probably take the second derivative from the very top version here when it's expanded. I don't want to have to use the product rule. So negative 15x to the fourth becomes negative 60x cubed plus 30x to the first. And now I'm going to just copy that and paste it down below here where I can use it. And again, that's not the most useful version. Even for plugging into, I'm not interested in finding the PIVs, but I still want to factor it because I don't want to have to plug it into there. So if I factor out let's factor out just a 30x, I'm left with, let's do a negative 30x. I get a 2x squared minus 1. And I kind of like that version. If I wanted to find my PIVs, I could set it equal to 0. But I'm after something different here. I have 3 critical values, 0, -1, and 1. I want to know what the sign of the second derivative is at each of them. At what is f double prime and -1? I didn't write that well enough. Let's do it again. What's f double prime and -1? What's the concavity at one of my critical values? What's the concavity at the other critical value? And what's the concavity at the third critical value? Okay. Now, if I plug in my -1, let's see what I get. I get Negative 1 squared is positive 1. 2 minus 1 is positive 1 times positive. Positive times positive is positive. Now here's the justification. Let me come down here. We said it was positive. It's all about the inequality when you're doing the justification. So here's your argument. Since f double prime of negative 1 is positive, I like to do this. Positive, positive, that means you're smiling. That means it's a what? A local min. I see people mess it up. They think positive, they're thinking high. When I'm positive, I'm high. I'm like, whoa, I'm way up there because I'm happy and I'm positive and I'm high. So it's a local max, but it's not. Okay? So draw it. Positive means you're smiling. It's a local min. So here's all you have to say. F double prime of negative 1 is greater than 0. So F has a local what? Min at x equals negative 1. The sentence is a little bit shorter. The justification is a little bit shorter. That's one advantage the second derivative has. All right, let's do F double prime of positive 1. Well, you plug it in, you're going to get positive times negative, which is negative. That's less than 0. So F has less than 0. I better draw it. Less than 0, that means I'm frowning. Draw an X on the top of his lip. It's a local max. So F has a local max at x equals 1. That's it. That's the justification. Pretty nice. If you plug in a 0, you're going to get 0 times negative 1, which is 0. What does 0 mean? Right? 0 means Test doesn't work. Inconclusive. It means it could be a local max, could be a local min, could be neither. You just have to try another method, which means you got to back up and do what? The first derivative test, which in this case it turned out to be a neither. Sometimes it might still be a local max, sometimes it might still be a local min. But 0 for the second derivative test means inconclusive. Try something else. All right, so I probably would not have used the second derivative test there, even though the second derivative was pretty easy to obtain. It was just a power rule, right? Especially in hindsight when I had to go back and do the first derivative test anyway for one of them. But when might the second derivative test be a preferred method? Hi. When it says to use the second derivative test, as on part B, then it would be required, like if the instructions say use log differentiation to find the derivative of x. Right, then you have to use it. Good answer. Good answer. Well-trained student. The other time where it would be more preferable is when you don't actually have an equation. Because remember, the first derivative test requires you to choose arbitrary values on either side of your critical values, and you must then plug those into some function to generate the sign of those values, right? If you don't have an equation into which to plug, you're kind of out of luck for the first derivative test, right? The second derivative test then is useful because it only requires information about the curvature at that same point. It doesn't require any knowledge or information to the left and right. All right, so let's look at example 6 and we'll stop here for the day. Selected values for a twice differentiable function f of x. What does twice differentiable mean? The second derivative exists. So if a function is differentiable, it is continuous as well, right? We know since it's twice differentiable, the first derivative exists. So the first derivative is also continuous. Yes, yes? Yes. Okay. Part A. Is it safe to say that f of x is concave up on the interval from -3 to 5? Well, high or well, high not? Well, let's see. Here's -3, there's 5. Second derivative would be concavity information. Hey, look. It's concave up at -3, it's concave up at 4, and we run out of concavity at 5. But we're looking on the open interval. So the only value that I have the concavity for on the open interval from -3 to 5 is +4. That's a positive number. Ergo, the function must be concave up everywhere because it's concave up at one point. If it's raining outside my window, the left one, it must be raining outside every window, right? Is that true? No. So we can't say that. No. Silly. Can you add that? Sure. No, silly. It's not safe to say that because we have no F double prime info for any points other than at x equals 2 on the interval from -3 to 5. Or something to that effect, right? We only know on the interior the concavity at a single point. And by the way, there are infinitely many points between -3 and 5, and we only have one of those, so we still are missing infinitely many points. And no, we're not going to take that bait and overgeneralize, right? That's not us. Part B, explain why there has to be a z from -3 to 5 such that f of z equals 6. You might be like, oh, z? My teacher never taught me about z's. I'm just going to skip it. He never talked about z's. Right? Well, if your teacher never talked about z's, that's not your calculus teacher's fault, right? That's your elementary school teacher's fault. Because what kind of alphabet song is it if you don't finish the song at the end? Elemental P, Q, R, S, T, V, W, X, Y. Now I know that would be a horrible song. What is z in this case? It's just a what value? An x value. And we're trying to prove that a y value exists. Which theorem do we use to prove that a yi value exists? The IVT. This is an IVT question. So, the IVT, remember, just requires us to figure out the y value at the endpoints. And this is easy. We just pull them from the chart. F of -3 is 0. And f of 5 is 7. Okay? So since the value we're looking for, 6, is in between 0 and 7, and f is continuous, this is a big part of it, on the closed interval from -3 to 5, comma, by the IVT, comma, and then you're just going to reuse all of their words. Remember, this was taken from the 2007 exam where the average was less than 1 point. Okay? Now, we're not going to be able to finish, but part C I think we can get. Explain why there has to be a W such that f prime of W is 7/8. When you're trying to prove a slope is in Algebra 1, mx plus b, it's the m, right? It's the French verb m, monter, to climb. So when you're trying to prove that a slope exists, you're going to use the slope VT, right? Or the MVT, okay? So the MVT then would say that f of 5 minus f of -3 over 5 minus -3 has to equal f prime of x for some x on the open interval. Well, we can pull the values from above. That's going to be 7 minus 0 over 8, which is, OMG, 7/8. That's f prime. We showed the work. Now all we have to say is, since f is continuous on the closed interval, and what? What else is needed for the MVT? Differentiable on the open, -3 to 5, comma, by the MVT, comma, and then you reuse the words. There must be a W such that blah, blah, blah. And there you go. We'll finish D tomorrow for this example, which is kind of what I'm getting at for this whole section, why we have to use the second derivative test as opposed to the first. And then we should be able to finish tomorrow, so it looks like we're looking at a Thursday worksheet due date, unless you're not here, and then I guess you can still submit it. Yeah. Okay. So, anyway, have a great rest of the day. True.